Hello, this is my Lab 1 submission covering constant velocity. So in this lab, we investigated the motion of an object moving at a constant velocity. The purpose of this lab was to understand the relationship between a position and time for a uniform motion, and to verify that a constant velocity results in a linear position time graph. The fundamental physics principles behind this is we use this kinematic equation right here to calculate the position of the object using its initial velocity and its constant velocity times the time that it's moving. A brief overview of this experiment is we tracked a motion using a tracker over time. We recorded the position values at different time intervals compared to the experimental motion to a computational model. The goal was to confirm that position changes linearly when a velocity remains constant. So the system plus surrounding, the system was the object moving. The surroundings could be the table that the object was moving on, the surface, so frictional forces acting on it, and maybe some air. But the system was treated as the surroundings of the system were like negligible because they don't really make that much impact on an object. So this is the experiment setup. We used a moving object down here, a tracking software to track how it was moving, and a meter stick to show um, the distance that it moved. Procedure, we place an object at initial position. We move the object with a gentle push. We measured the position of the object over time. The data was entered into a computational model, and experimental and simulated results were compared. This was the data that we got. Kind of looks like a linear graph. So this is the position time graph. Kind of shows like it's a constant velocity motion. This is the code we used to obtain the data. So it's a calculation loop. We found the time that it took for the object to roll the distance, which was about 0.72 meters. We assumed there was no net force acting onto the object, and we used a update position um, formula to track where it was in the computational model. This is what the computational model looked like. It's a perfectly linear graph, as it should be in a computational model. We assumed that it was a constant velocity, no acceleration, and negligible friction acting on the object. So this is the results plus explanation of like why it's acting this way. So it's a delta x, so delta position, change of position over the change of time, and this would result in the velocity. So if you looked at that graph, you could tell that since it's a linear graph, position time graph, that the velocity would be constant. So this is what it looked like. So predicted slash observed. So this blue line being the observed position. You can see how it kind of slows down compared to the constant linear graph right here of the computational model. This is due to friction, other things acting onto the object. It could also be human error, as we see in this other slide. So it was kind of hard to track the object using the tracking software, but it's an experiment. Things happen. And of course, a slight friction on surface with other forces acting on it. As a conclusion, so we decided that this was sufficient evidence to show that an object moving at a constant velocity produces a linear relationship between velocity and time, proving this kinematic equation right. So the questions we got that if the axes were flipped in the tracker, what would happen? So if the numerical values of the position, so the numerical values of the position and velocity would change sign. This would mean that if it was moving in the x direction originally, it would move in the negative x direction. So that would make velocity, instead of being positive, it would make it negative. So, and then what kind of happened, like what kind of forces are acting on the object? We know that there are forces acting on the object. Like there is a normal force keeping the object on the table. There is a gravitational force. There is a frictional force, but these forces are canceling out or so negligible that we don't even count it into the um, what's happening onto the object. So that's going to be my lab submission, and thank you for watching.